Hey, good morning, everyone. Welcome. We're thrilled to extend our warm welcome to our third online webinar of the year. And this time we'll be focusing on a crucial aspect of the industry efficiency, and this is steam system diagnosis. Yeah. So as we know, in today's dynamic industrial landscape, optimizing steam systems is paramount for enhancing productivity, reducing costs, and ensuring environmental sustainability. So as industry leaders, we recognize the significance of staying ahead in this ever-evolving field. Yeah. And thus we're delighted to offer you an opportunity to delve deep into the intricacies of the steam system diagnosis. Yeah. So maybe Nick can go next. Okay, so here it's great pleasure to introduce Nick Wisby, who's going to be our presenter for this insightful session. And Nick is an expert within the field of with a wealth of experience, and he will guide us through this journey. Yeah. So as you know by now, some of you, he is a dedicated and results-oriented technical sales support engineer with a rich background in the engineering industry. Yeah, with over 2 decades of experience in technical applications, electrical engineering, control and instrumentations, and STEAM. He's been part of Spirax Sarco for over 7 years and is now based at Spirax Sarco East Africa office. Yeah. So with his extensive knowledge and practical insights, Nick will illuminate the nuances of STEAM system diagnosis, offering invaluable strategies and best practices to maximize efficiency and performance. Yeah. And today, in today's, I will be your producer. I am Anthony Macharia, the sales manager for Spirax Sarco East Africa, together with Cornelius Schneck, who's the sales national manager for Spirax Sarco South Africa. So, and a bit on housekeeping. So this session will be a total of 75 minutes. This is 1 hour presentation with a Q&A, 15 minutes Q&A. All of your microphones will be muted throughout the session. And would like you to submit the questions through the Q&A panel function, which can be found on the webinar's dashboard. Yeah. So the questions will only be seen by the host. Yeah, and it may not be possible to answer all the questions during the 15 Q&A session, but we will reach out to everybody after the session to ensure that all of your questions are answered. Yes. So I would like you also to really please to complete the feedback form after the webinar, and we will be able to get back to you using that form. Yeah. So in this slide, this is how you will be able to do your Q&A. Yeah. So you will see a Q&A live event tab where the moderator will publish. This is I'll be able to publish your question, and it will appear on everyone's featured tab along with the answer. So I would advise you to type your question in the compose box and then click select send. Yeah. If you want to ask your question anonymously, please select post as anonymous before you click send it. Yeah, if you don't want to show your name. Okay, so up to that, I believe I'll hand over to Nick, who will take us through this session.
Thank you very much, Anthony. Welcome everyone, and thank you for joining our third webinar of the year. So in this one, we're going to cover the who are Spirax Sarco, then control valves, steam quality, corrosion, stall, flash steam losses, poor heat transfer, and water hammer. So all of these hopefully are things that you'll be familiar with, you would have seen on site, and we'll tell you how to diagnose them, but also how to fix them. So first, who are Spirax Sarco? So we were founded in 1888, so we've been around for about 130 years by 2 gentlemen called Sanders and Reinders under the name Sanders, Reinders and Co., which later formed the Sarco of our name, so the 2 names put together. In 1932, we started manufacturing in the UK under the brand name Spirax, so that then gave us the company name of Spirax Sarco. So we operate in 145 countries, 145 operating companies, 180 plus local sales offices, 55 countries served by distributors. We have over 10,000 employees now and over 2,000 local service engineers. We have 29 manufacturing sites on 4 continents. Our HQ is in the UK in Cheltenham, and we have 59 customer training centres around the world. So we have now rebranded our name from Spirax Engineering to Spirax Group, under which we have these companies. So Gestra, many of you would have heard of, Cotopaxi, which deals with our digital offerings, Spirax Sarco, of which I work for, and then we have our Electrofit solutions or electrical thermal solutions under Chromlux and Thermalux. We own Watts and Marlow, and as it says here, we're a FTSE 100 company with turnover of £1.4 billion a year. I think it's actually higher than that. I think it's about 2.4 now. Over 30,000 products and a global footprint. These are the main product areas we offer. It's not exclusive though. So as you can see, we offer boiler controls, clean steam, humidification, steam traps, which most of you would know. We also offer many services such as 24-hour priority response, steam quality testing, and valve reconditioning. So we don't just want to sell you new products all the time. We want to fix the ones you have too. And what makes us effective at this is we actually have boilers on our site. So this particular boiler is in our training centre in the UK. We service it, we fix it, we do all the works on it, and we train on it as well. So we have practical knowledge of boilers. So we now come to common problems, causes and solutions for control valves. So first, Bernoulli's principle. Bernoulli's principle effectively is a fluid dynamics. It states that the increased speed of any fluid will decrease the pressure and decrease the fluid's potential energy. So as you can see here, if you imagine that this is a valve seat, as it comes through your pipe on your inlet, it then is reduced by the orifice of the control valve, leading it to speed up, which gives you a pressure drop. And then when you get to your outlet piping, it then returns to its normal flow. This means that on these areas here, you can get superheating, but you can also get flash. So if it was, say, water valve for a pump system, for this drop in pressure, you could get flash steam here, and that's why you see the corrosion on control valves for water or for pumps. So here, as it shows, low velocity, high pressure, high velocity, low pressure, and returning to low velocity, high pressure again. So what does that do? So poor control of temperature process, excessive erosion, maintenance of seats, noise, vibration, tripping high limit valves, relief valves. So I'll go through these points individually. Poor control of temperature. So if you have, say, a cooking process and you're not controlling the steam properly, you're not taking account for the velocity changes, the process may not have the temperature you require to meet. We'll see excessive erosion and maintenance of seats. So the faster the velocity through the valve, the more erosion you'll have on the valve seat. So we recommend, if I just go to the next one, we recommend on these nominal velocities for things like in any control system. So wet steam would be 40 meters per second, dry saturated steam up to 150 meters per second. However, these last two figures I would suggest is for a control valve only, so it's not for your system. And superheated steam 250 meters per second. So likely causes of these overall too high velocities can be oversized control valve, wet steam, heat exchanger stall, and high outlet velocity. Do we have any questions at this point?
Not yet.
Okay, guys, join in, throw your questions in. We live for the interactions, so we very much enjoy your questions. So, solutions for control valves. is replace a control valve with the correct sizing. So we can guide you through that. We can size control valves. If you give us your pressures and your flow rates, we can size the valve seats accordingly. Install, maintain and repair the separator. So a separator before the control valve will drop out any wet steam or any droplets from your wet steam, increase your dryness factor and protect the equipment which is downstream from it. So how the separator works, as you can see here, you have your steam coming in on your inlet. It hits a plate. The water that it's carrying, the droplets that are carried in that steam will hit the plate and then work their way down through for a trap set. Steam goes over the plate, comes back throughout your outlet at a drier consistency. So install, maintain and replace insulation. So the last thing you want to do is lose heat through your pipes. Pipes, because heat is energy. Energy has just cost you from the boiler. So we want to maintain as much of that energy as possible. So good insulation in good working order is essential to your steam system. Install reduced internal trim to the valve. So we want to speed it up to dry the steam out. So sizing the valve correctly again. And install low noise trims to valves. So that will reduce the noise, reduce the vibration, reduce the wear and the erosion. So common problems and causes for steam quality. So we have many different grades of steam. Depending on your process will depend on what you're using. So plant steam, normal steam coming through filters, just your normal strainers. These things are used for, as it says, high vac, laundries, pulp and paper, petrochemicals. The food and beverage industry will use filtered steam. So we use our stainless steel filters with say a 5 to 25 micron filter to take out any particles that may have formed in the steam. Particles are mostly from erosion, so rust in the pipes, carryover from the boiler. We try and catch all of those and filter them out. With the filters, especially for food and beverage, to reduce cost, you would have these as close to process as possible. So pipe work after a filter should be stainless steel because it aids in the purity of that steam, or if not being able to rust and so on. But stainless steel piping and equipment is expensive. So the closer you can put this to the point of use, the cheaper it will be for you in materials. So if we have, say, a cooker where you're using steam to inject in and heat a food process, we would recommend that all the reduction just before it goes into the machine and to the point of use, so the last few meters, was all stainless steel after the filter. Before that, it can be carbon steel. Hospitals, they will use clean steam. So again, it's more filtration. We're talking now RO water in systems, clean steam system loops for hospitals, cosmetics, life sciences and food and beverage. And then you've got pharmaceutical and biotechnology, which will use ultra pure water, so demineralized water in their system. All stainless steel pipe works because the steam is most likely directly injected into product. Does anybody have any questions at this point?
Not so far.
Okay. So causes of contamination. So particulates coming from your water softener, raw water in. Chemicals that have been added to the water to cleanse it. Boiler carryover. So if your boilers are running inefficiently, you can get carryover of those chemicals and that polluted water into your system. Pipe scale. So from the carryover, from the water residue, you can end up with scale, corrosion. So next one is corrosion. So damage to those pipes, rust from the carbon steel particulates being picked up in the pipe, and cross contamination. So if you have a leaky cooking vessel where there is a cross contamination between the condensate and the steam, that can be carried over into your feed water or then make its way into the boiler. So all of these we want to protect against. So install users of clean steam. So this gives you the different grades of steam and the different processes that are going to be there. So the application, as you can see, so you've got the CIP, SIP, clean rooms. So where you will see these in what industries? So CIP, for instance, you'll see in pharmaceutical, brewing, food, cosmetics. Clean rooms, humidification, mostly found in pharmaceutical industry and healthcare. Sterilizers, autoclaves, again, pharmaceutical and healthcare, so hospitals. Bioreactors, pharmaceutical. Jacketed pans, pharmaceutical, and I would say it should be food. Yeah, it's in cosmetics. I think it should be in food too. Filling of so it's pharmaceutical, brewing, and cosmetics. Sorry, and food. Direct injection, food industry. Pasteurization, again, food industry. Bottle and keg sterilization in brewery and food. Jars, bottling and filling, so food industry. Cooking, food industry. Skinning, peeling and blanching, so removing the skin on, say, vegetables or fruit, food industry again. Humidification, proving, so bread, those kind of things, food industry again. Laundry will be used in healthcare. They need to clean the scrubs. CS and PS generation, all industries. And distribution, all industries again. Steam filtration, mostly found in brewing, healthcare and food. The reason why we're not showing pharmaceutical on steam filtration is because they tend to be clean steam loops. So again, as we were speaking, demineralized water, where the water is actually different to your standard boiler. It's a closed system and there tends to be very little, if any, return of condensate. Any questions at this point? No?
No.
Sorry, actually, I didn't. Yeah, okay. Yeah. So poor steam quality equals wet, scale, rust, and particulate. So the problem is process contamination. So the insulation at heat transfer, extended process time. So this says that if you have any insulation in the pipe between the steam and what you're heating, that could be from air, or it could be from scale, it could be from burnt product. It's going to extend the process time, how long it takes to heat the media you're trying to heat. Increased resistance, problems in process. So again, if temperature is very important in your process, say it's a cooking process where you need to maintain a certain temperature, I could think that would probably be in the milk industry in particular as well. Then the resistance, the extra insulation that's there, is going to cause an issue on you reaching process temperature. So the problem you have with pumps is increased maintenance of strainers, increased maintenance, erosion and corrosion. So all of this from the carryover or from pumping the media around. Likely causes, so poor control of steam boiler. So if you're getting a lot of carryover, if you're flattening the boiler, so effectively decreasing the volume of steam in the boiler, it's going to give you issues with chemical carryover, loss of steam, loss of temperature. Poor raw water quality. So if you are not removing the total the particulates in the water, such as high salt or any other scale that's in the raw water, any other contaminant that's in there, that then carries over into your boiler, which could potentially carry over into your steam system. And poor water treatment, as it says. So a lot of times we'll use these epoxy tanks, the resin tanks, to add salt to remove particulates. If you're not treating your water properly, again, it makes its way to its boiler. Then it makes its way to the steam system. And wet steam, so from bad insulation, from poor quality steam, wet steam will introduce water into your lines. Water has a lower enthalpy than steam, so it's giving out less heat, which makes your system less efficient. So the solutions: install and upgrade, maintain separator. So as we were speaking, as we've talked about the separators are important. Separators are cheap in comparison to, say, control valves and other equipment. So to install a separator before a control valve would be best practice, simply because you want to maintain that control valve and make sure that you have to repair it as little as possible. As I said, control valves are expensive. Protect the equipment you've got. It's the same reason we wash our cars and we hoover our seats. We try to keep clean and in good working condition our cars. Same for your steam system. So reducing heat loss, improve insulation. We covered it again. If you've got a crack in your covering on your insulation, which is allowing water in, say from rain or from condensate, so condensation rather than condensate from the steam line, it's going to absorb heat from your steam system. It's going to cool your pipes. So therefore it's going to introduce wet steam into your process, but it's also going to cost you more to run your boiler. So check strainers orientations. So as we've covered in previous presentations or webinars, strainer on a steam system should be with the strainer facing towards you horizontally. I will show it shortly. This is so that it can't gather any water, so create a water slug or a pellet that goes down the line. For a condensate system, you want all the particulates to drop out of the condensate, so the strainer will be facing downwards, so it's vertical. This allows you to capture the particulates and remove them from the condensate before it's returned. Upgrade boiler blowdown and level controls. So if you have poor level controls, if your boiler blowdown is erratic and not blowing down enough, you're not getting rid of the sludge and the TDS that's in the bottom of the boiler, in the boiler itself. So again, you're introducing elements that can be carried over into the steam system. All of these will affect the efficiency of your steam system, which again will cost you more on your boiler. You will have to maintain your boiler more, you will have to burn more fuel, you'll have to flatten that boiler more often. All of these are to lower the costs that you're incurring on sites. So as it says here with controls, consider fitting steam filters, upgrade to clean steam. If you have a process where steam is injected directly to process or to product, the minimum grade should be filtered steam because of the human consumption element. So we would recommend the upgrade to either clean steam or filtered steam, depending on your process. Any questions at this point?
Yes, we do have two questions. So
yes.
The first one is how to prevent process contamination. How do you prevent process contamination?
So the easiest way is routine maintenance. So the way to check is to check that your equipment is working properly. Routine, say every 3-6 months, depending on what schedule you have and what kind of usage you have on your system. It's always better to do preventative maintenance than when something goes wrong. If I have a control valve which I know is starting to pass, maintain it then. Don't wait until it fails. Because you're protecting not just the control valve, but everything after that control valve too. So the simple answer is maintenance, routine maintenance.
Okay. Okay, thank you. And the second question is there any solution to heavy scale buildup? Yeah, or is this only solution replacing the affected pipework?
So you can use various different caustics to clean pipes. I believe CIP is a caustic as well, so that's effectively what it's doing. It's cleaning any residues, any scale that may be present in the pipe. It would depend on the strength of the caustics you're using. The best prevention, or the best way to sort the problem is prevention. So I would suggest that you need to look at the carryover you're getting from your boiler, the quality of water that's given to the boiler itself, and the chemical use. So maybe you're overdosing on chemicals, that's giving you more carryover, or the water itself is quite hard, so that's bringing scale over. It depends what that scale is. Are we talking products? So it's a steam line, so we're going to be talking about water scale, I imagine. Again, caustics are designed to remove those scales. Hopefully that answers that question.
If so.
Yeah. So, sorry, was that the last one?
Just another one has just come in. The question is, what is the advantage of having a modulating water level control compared to an on-off for the boiler control?
So it's
Which
the
one would
difference
you recommend?
effectively. Yeah, so if we talk at a control level, so we're talking the actual controllers that control these valves, they work on either hysteresis or window. And what that means is if you have on-off control, you have a low level which activates the pump and it doesn't turn off until it reaches the high level. That means, again, it doesn't then turn back on until you reach that low level again. So you're dosing large amounts of cold water into a boiler. If you have hysteresis, which is effectively 4 to 20, so it's just modulating control, it's maintaining a level. So the water that's being introduced into that boiler at one specific time is a lot less. So it means you have less thermal shock to your boiler, so less heating times for reproducing steam after you've introduced more water into the boiler. It's a little bit of a trade-off because a modulating pump and modulating controls will always be active, whereas on-off will be running then stop. So depending on your process, you can be using more power because you're running modulated control, but it depends. But you'd be running a more efficient steam system. So it depends what is costing you most. Hopefully that answers the question. Any more
I think so.
that have come through?
No more questions for now, so we can proceed.
Okay, some very good questions, guys. So please keep them coming. So common problems and causes and solutions for corrosion. So corrosion in your pipes and products. So the problem, corroding, failing steam trap internals, corrosion in steam trap bodies, corrosion in condensate return pipes, increasing water treatment chemical costs, increased boiler blowdown. So many of you, I imagine, would have seen some of these at some times. So we're going to cover how to solve those. So the cause, poor air venting. So if you've got air trapped in your system, you will cause carbonic acid with the CO2 that's available there with water. That gives you erosion. Excessive stop-start boiler. So again, referring to the question we just had about on-off control with water. Stop-start, this could be on your boiler. So it will be running harder when it has a thermal shock, so a cold water load added to it. So it's burning more fuel. That means that you have peaks and troughs when it comes to your steam production. Excessive stop-start of process, again, a similar thing. So if your process is running, all our processes on all our sites will run and stop for a period of time. But what this is talking about is, say that's doing several times in an hour, and that's going to give you excess wear. Poor water treatment, as we covered before, so the particulates that you find in that water, and poor boiler blowdown control. Again, we can never eliminate all particulates in water unless you have a pure steam demineralized water system. You will get particulates, which means you will need to blow down. So you remove that sludge which is at the bottom of the boiler, which normally accumulates around the fire tube, so that would then prevent the heat transfer to water from the fire tube. So boiler blowdown, that's removing that sludge, removing that excess particulates in your boiler, so that it doesn't carry over, but also so you get more efficiency in your steam system in the production of steam. So solutions, we can fit and repair air vents. So air vents, I would say, are very essential to your system, especially with when we use vacuum breakers too. So it's slightly off topic, but many of you will find that you have leaking gaskets on systems. So when your system's firing up and when it's running, you'll see that you've got leakages between the gaskets, between flanges. Most of the time, or a lot of the time, that can be cured by adding air vents, not excessively, just one or two. What happens is when you're cooling down your steam system, the steam collapses, which pulls a vacuum. Now, what's needed to fill that vacuum is normally air. The steam system will look for the weakest point in your pipework, which usually is the gasket in between flanges, and it will make them leak. It will pull the air in through that gasket, cracking the gasket, causing damage to the gasket. That means when your steam system then fires up, you've then got a leakage path for steam too. So by installing air vents to remove the air, but vacuum breakers to add the air when the system is cooling down, you will prevent the wear and tear of gaskets and leakages. So as it says here, select the appropriate steam trap type. So we have many different steam traps, all of which we have for different applications. So for instance, if you were doing heat tracing, you want, in the oil and gas industry, for instance, you probably wouldn't be returning that condensate. So you would use something like a biometallic trap, because that will introduce what we call a cooling leg before the trap. So there is a volume of water, maybe 1 or 2 meters, sat behind the trap before it's discharged. That allows you to remove as much of the heat as possible before you get rid of that condensate. However, if you have a process that's, say, an autoclave, where you need an oven or a rotunda or whatever else, that you need to have as pure steam or as hot steam as possible with no air, no condensate, you would use something like a flow trap, where you want to remove the condensate quickly in large volumes, so that you get the maximum heat transfer. Check water treatment regime. So again, with checking the quality of water in your boiler by boiler tests, checking the water quality as well. The more you check it, the more accurate you can be with your chemical treatments. And upgrade of boiler controls. So this refers again to the on-off controls versus modulating. So at this point, do we have any questions? So anything through there, Anthony?
Yes, I think we've just had one question. So what are the main reasons for causing air vents leaking?
Leaking. So it depends on, so effectively all it is a disc, or I think it's a biometallic capsule actually in these with a ball, isn't it? You can get over expenditure from heat, you can get particulates on the valve seat itself, or you can get general wear and tear. These are metals that are expanding and contracting over time. If they've been there for a while, at some point they're going to lose the elasticity. Sorry, I can never say that word properly. And they're just going to fail. Maintaining them, just like anything else, is if you're maintaining the trap, these are a form of trap effectively. You should be maintaining these at the same time. It is much cheaper to maintain equipment than having to buy new. I think we estimated 30% compared to the cost of a new equipment. So if you're spending £100 on 100 Kenyan shillings, let's change that to replace a piece of equipment, to repair it you will only spend 30. So it makes sense to do more preventative maintenance. Hopefully that answers that question. Any more?
Yes, there is another one. Can you elaborate more about the boiler start stop can affect belief?
Yeah, sure. So effectively, as we were saying, with window control, so what window control is effectively you have what they form as a square on the control, which is a low level where the pump activates and a high level where it turns off. So that forms a window, a band effectively. So when you use on-off control on a boiler, say you have a 10-ton boiler and you're introducing 100 litres of cold water each time this pump is turning on and off. Don't quote me on these figures, these are just the examples. You have 100 litres of cold water which is no longer at steam temperature being introduced into that boiler. So you're introducing what we call thermal shock, and that is effectively cold water, cold comparatively, water into your boiler, which then needs to be heated to steam temperature before it will produce steam. When you have modular control, it's effectively, I'm trying to think of an example. You're maintaining a level on a tank, for instance. So your feed tank, I imagine there is a a level, maybe 1,000 liters or so, that you want to maintain and make sure is always there. So modulating control will do exactly that. So as the boiler drops in level, even fractionally, you have the control valve and the pumps activate, so it maintains a slower amount. So if you are introducing, say, 100 liters on stop-start, on-off, you'll be introducing, say, 1 liter on modulating. So the thermal shock to that boiler is less. It only needs to heat 1 liter of water, so it makes it more efficient. I'm hoping that explains it enough.
Yes, so so we also do have another question. Is how does the material selection for steam system components influence corrosion resistance?
So yeah, I mean, it can make a lot of difference. There is what we refer to as dairy grade in Europe, which would be stainless steel 316. It's very hard wearing, doesn't rust. It will be subject to erosion, but at a slower rate than, say, carbon steel, because it's a harder material. All these, if you're using SG iron, for instance, SG iron is toroidal graphite. It has a graphite that allows elasticity into the material. So when we talk about wear and tear, if we talk about microfracturing and pinholes, SG iron is less likely to see that in compared to iron. Iron being quite a ferrous material, being quite soft, it wears quickly, it picks up particulates, and it's open to microfracturing and pinholes. So material plays a massive difference in the erosion and the corrosion you're seeing in your system. Therefore, the particulates that are being gathered in your strainers. But we do appreciate that stainless steel is expensive compared to, say, SG iron, cast iron, carbon steel. So I would suggest that if you have a clean steam process or a filtered steam process, you minimize the amount of stainless steel you use, so you take it as close to process to end of use as possible. So your whole steam main can be carbon steel, for instance. If you're only using, say, the last 3 or 4 meters for your PRVs and your pressure reduction near process, make that stainless. Don't make the whole system, and you'll reduce cost. Hopefully that answers that question.
Yes, I do believe.
Any other questions?
We currently don't have any other questions, so I believe you can proceed. And thank you guys for bringing up the questions.
Yeah, we very much like. Yeah, we very much like your participation. It makes it much more fun for us as well. So please keep those questions coming. So common problems and causes and solutions for stall. So many of you had seen stall in your heat exchangers, for instance. So the problems, what it causes, so erratic temperature control, so extended process times, as we said, product spoilage, so you're having to dump product, energy inefficiency, so again, that's referring to more heat up times, hunting of control valves, so where you see a control valve moving up and down more than you would expect it to, we call that hunting. So that will lead to excessive maintenance, steam leakage and loss inefficiencies, and product spoilage again. If you can't maintain the temperature because the control valve is hunting, it's going to spoil product because you can't guarantee the temperature of use. Corrosive condensate, so excessive maintenance, pipework, corrosion, rust, cross-contamination, increased chemical dosage costs because you then got to remove that contamination, and increased blowdown. And as we touched upon earlier, heat exchanger failure, increased maintenance downtime, replacement costs. So causes can be insufficient differential pressure, so what you have on your inlet coming to your outlet. I will touch back on that in a second. Increased back pressure on trap and reduced heat demand by process. So I'm not sure how many of you have seen a leaking heat exchanger in your process. Often, not always, that is caused by stall. So it's where you get a backup of water in your heat exchanger and you reach a point, say it's 50% full of water, just for sake of argument, and 50% full of steam. Where the steam meets the water, there is going to be a difference in heating temperature. And again, through the water, it will heat differently to the steam above it. So that leads to warping, to damage to the plates that you find in a plate heat exchanger, because they are effectively expanding at different rates. That then leads to leaks. Overall, eventually it leads to damage. You have a higher pressure in the water than you have on, or compressive pressure in the water than you do to steam, all of which will slowly over time damage your heat exchangers, lower their efficiency, and create damage to where effectively condensate is where it shouldn't be. The back pressure on traps, so it refers to the, effectively, if you see a higher outlet pressure than inlet pressure, you're going to get stall. On a heat exchanger, again, because it's very easy to demonstrate, when you have a control valve to control temperature on a heat exchanger, so it's sat on the inlet just before the heat exchanger, it will modulate with the temperature. So it will control the temperature by opening and closing. As it closes completely, when it reaches temperature, the steam after it will collapse and create a vacuum. And that can cause stall, because then the inlet pressure is lower than the outlet pressure. So it backfeeds the water into your heat exchanger. Ways we can get rid of that are by pump traps, and other means, which I will cover shortly. So as it shows here, stall. So this is heating elements for heating air effectively. We are in East Africa. I imagine there's not a lot of air heating systems here, but this is a very good example. So here you've got -5°C air coming in. You've got steam coils going through the vent, and that heats the water, heats the air by radiant, allowing for 25°C out. You have to remove the condensate that's forming because it's giving up its steam, it's giving up its heat, it's giving up its enthalpy. So you need trap sets to remove that condensate. So I don't know if that's a repeat of the story. Sorry. So what you can find is, if you have a short area here, let's say this is only 30-40 centimeters, you can have a filling up of condensate behind the trap because it's trying to clear it. And that then leads to different heat transfer rates. So you may not reach 25°C here. The ways we can do this on this particular here, so if this air vent is, say, up by the ceiling, move these traps as close to the floor as possible. So you increase the distance here. By doing that, you increase the head pressure above the traps, and you will effectively keep the inlet pressure higher than your outlet pressure and allow the traps to work and clear the condensate. So as it says here, reducing back pressure on the trap, so you can fit the vacuum breakers, as you were saying. So where you have the collapsing of steam after the control valve on a heat exchanger. I know I referenced the heat exchanger, but it's quite visual. Most of us understand how those work. If you put a vacuum breaker after the control valve on the heat exchanger, when the control valve closes, the vacuum breaker will then break the vacuum that's there and maintain a higher pressure on your inlet. And then the air will then clear. You need a air vent on that with that vacuum breaker to clear the air you've just introduced when the control valve starts to open. And pump the condensate. So we do things like our pump traps, which here is the APT. How this works is it has a motive steam connection. So if the pressure on your inlet drops and the outlet pressure is higher, motive steam is introduced by the mechanism floating to the surface effectively and opening the port. That introduces steam into your system, making the pressure higher on the inlet, and pumps away the condensate. The other option here is a CRU, so a condensate return unit. Effectively, this is a large tank which 2 electric pumps. Once this reaches a level on a level sensor, the pumps will activate and start pumping the condensate. So the overflow, the U-seal, I've been to many customer sites where this is quite short. So we would recommend that you make this U-seal as long as possible. The reason being is that in here, we keep water as a seal, as a plug. It's simply for overflow from the the receiver. If this is too short, you will find the pressure of the steam here will blast this plug out, and what you'll see on site is you'll see steam venting from here. That's usually indicating that the water seal is gone, potentially because the U seal isn't long enough. So at this point, do we have any questions?
And no, not yet. So
No?
we can proceed on. Yeah.
So common problems, causes and solutions for flash steam losses. So as we've said before in our last webinar, the majority of what you'll see in your condensate system isn't actually water. So as we show here, you have 13 kilograms of steam based on 100 kilograms and 7 bar, 13% flash. Well, what that really translates in volume is 99.6 of the total volume is actually flash steam. Only 0.4% of the total volume is condensate. So what we're transporting back to our feed tanks is mostly flash steam, not actually water. As you can see from the graph, this will give you the figures. So as it says at the bottom here, condensate is the only liquid at suitable pressure. So because of the pressure temperature relation, we at 7 bar, if we heat it past, then we'll produce steam. But at 7 bar temperature, it's both steam and condensate at the same time. So that's what we call the biphase. So flash steam losses, problems. So you see again here, many of you will see this on your site. So this is increased raw water consumption because you're having to produce more steam. Increased chemical consumption, again, because you're having to produce more steam. Increased energy consumption. Like I said before, you're making more steam. Increased CO2 penalties, that's probably more for the European markets, but some of your industries will have to pay fines depending on how much CO2 you're producing. Decreased condensate return, so therefore the temperature that's going back to your feed tank is lower, you're having to do more heating. Decreased feed water temperature as it covers next because that hot condensate isn't being returned. Unsightly steam venting, so as this says, this could be a CRU with an open to atmosphere pipe, and you're losing steam because you're bringing it to atmospheric pressure. We can recover this steam as well. So causes, failed steam traps. If you have a steam trap which is passing steam rather than condensate, that's going to make its way down your line, probably to your feed tank, and you'll see steam venting from the top of your feed tank. Poor trap selection. So again, by choosing the wrong type of steam trap, you can cause losses. And poor trap sizing. So an undersized trap, an oversized trap, is going to cause inefficiencies in your system. For a general rule of thumb, when you are selecting the size of trap you need, you take the load that your process is using, so say it's 500 kilograms, and you double it. So you size a trap for 1,000 kilograms in this case. That's for cold startup. So as you start your steam system and you're warming up, you will produce more condensate than in any other time. So we recommend that you double the size of the trap from the load, as we said, so 2 times load to size the trap correctly. Failed condensate pumps. So if you're not pumping back condensate and you have no pressure to do so, it's sat there, it's not going back to your boilers, it's not giving that heat back to your feed water. And incorrect sizing of condensate receivers. So if your sizer is too small, you're going to have stall, you're going to have backup of condensate. It's not going to return as fast as possible. So you're going to see heat losses, various different other things. Is there any questions at that point?
Yes, currently I have 2 questions. The
Yep.
first one is, can you elaborate on the role of falling, scaling, or blockages in causing stalls?
So falling, stalling, yeah. So effectively, anything that increases the back pressure that's in a system. So if you've got a condensate pipe that's sized for a certain load, and you have scaling or you have any kind of buildup or residue on that pipe, you're reducing the bore that's there. Therefore, the pressure increases. The back pressure is going to increase. So that then will cause an issue with stall, or can cause an issue with stall. If you sized, say we have a float trap, with ours we have the FT14, then it's followed by a couple of digits. So we have, say, dash 4.5, dash 10, dash 14. So that's the figure afterwards is the maximum amount of back pressure you can have on the trap before it no longer works. So if you've got, say, a FT14 with a dash 4.5, so 4.5 maximum back pressure, there has to be a difference of 4.5 bar, minimum 4.5 bar between the trap and the condensate line, or up to 4.5 bar, sorry, between the condensate line for it to work properly. In any other position or any other pressure differential, the trap won't function properly. So you either might need a bigger one. 4.5 would be our smallest. So say you have a 10 bar differential pressure, you'd go for the FT-10. So correct selection of equipment. Back to the scaling, effectively, you're creating resistance. Anything that creates resistance creates back pressure. Back pressure is bad. You want to minimize it as possible. Hopefully that answers that question. Next one.
The next one is, are there specific techniques or instruments used to measure or detect the presence of flash steam?
Flash steam. So yeah, you can do it by heat, effectively. So we'll cover it on the next slide, but a trap that's passing steam, the outlet is going to be hotter than if it's passing condensate. So by measuring the temperature on there, you can tell if a trap is failed open. The other ones is mechanical things like, say, a sight glass. If you have a sight glass in a condensate line just after the trap, you'll be able to see the water passing through the sight glass. So water passing would indicate the trap is in good working order. Hopefully that answers that question.
If so, and then maybe, okay, for the last question is, can you provide examples of application where flash steam is used effectively?
Yeah, so say you have a CRU which is open to atmosphere. So you see that pipe on the roof and it's venting. You could use a flash recovery vessel to grab that steam and maybe pull it through, say, a heat exchanger or combine it with motive steam and use it into a process. So I'm thinking of something we looked at the other day. They have washrooms relatively close to where they're venting some flash steam. By adding a flash steam recovery vessel and then combining it with a CIP line, which is currently going to drain, we can then use that for a water-to-water heat exchanger and heat water for washrooms. You could use that water anywhere, effectively, but it allows you the water-to-water heat exchanger allows you to separate what is contaminated or unused or lost energy, and to use it onto a relatively clean media, so in this case water, and use that elsewhere in your process. So it could be for washdown stations, it could be for washrooms, as we've said, it could be to heat jackets on pipes, anything. It depends what you would use the recovery for. Hopefully that answers that question. Next one.
There are no more new questions.
Okay, yeah, so I'll move on. So again, as we've shown here, so the solutions, so steam trap audits. So we can offer an audit where we will attend site. We can look at the traps, diagnose if they're working correctly or not. We then tag them and then offer repair more than replacement. As a global company, but also global industries, the emphasis is more on replacement because it's less energy processes to manufacture. It's greener for the environment. So we try to lean on repair first, but occasionally we will have to offer replacement. So as shown on the screen there, you have the thermal gun that we were talking about. I think that's the thermal gun, or it might be the noise one. Then we have the steam trap audit and the flash recovery vessel on the far right. So steam trap monitoring, as we put there, checking the traps, making sure they're working correctly. Replaced with thermostatic steam traps. Again, that would depend on the process where you are, and the use of flash recovery systems, which again I said is the image on the far right. Just before I move on to that, I just want to make sure there's no more questions.
No more questions. You can proceed.
Yeah. So common problems, causes and solutions, this time for poor heat transfer. So the problem, what you will see on site: process quality issues, failure to reach required process temperatures, process time is extending. So if we think of that cooking vessel, as we were saying, temperature not reaching the required temperature means that the product can spoil. If it does, but takes longer to get there, it means that the cooking time takes longer, therefore you're using more energy. So the cause could be from waterlogging, failed incorrect trap selection, stall, as we've said already, insulating effect of scale on the heat exchanger, and wet steam. So wet steam will have a lower enthalpy. So the solution, we can monitor, repair and replace the steam traps, fit automatic pump traps to remove the stall, improve boiler control upstream. So that's talking again about the on-off control versus modulating, fit, repair and replace separators, and fit, repair, replace insulation. So again, I haven't touched on the separators and insulations because we've covered that earlier. But again, all these will help produce a more efficient energy system. So anybody have any questions at that point before I hit water hammer?
Yes, there's one new question.
Yeah.
So looking at the composition of condensate, that is 99.6% flash steam and 0.4% condensate, does that imply that it is not cost effective to invest in condensate recovery?
It's quite the opposite. So remember that those figures quoted are at 7 bar steam as well. The volumes change depending on the pressures, but steam has a higher temperature and higher enthalpy, or give up its enthalpy higher than what condensate will. So if say you're running a condensate return line into your feed tank and you're preheating water before it goes into your boiler, if you vent that condensate or you don't return that condensate, you're losing that energy to atmosphere. So you're having to pay more to produce the steam that you are. And the way we do that is by preheating the water. There is less of a difference between the usable temperature of steam and the water that's entering the boiler. So therefore there's less heating times, less energy used to heat that water in the boiler, and less chemical treatment, because remember, this condensate has already been treated. You've already removed a lot of the harmful components you get from the hard water that's coming, so the feed water from mains. So by returning the condensate, even when it's can be majority of it being flash steam, you're reducing the cost of chemicals, energy that you use, thermal shock to the boilers, all those kind of things. So as much condensate as you can return as possible means that your system is more and more energy efficient. So we would recommend that a feed tank temperature for an open to atmosphere tank would be around 85 to very high 80s temperature before it goes into your boiler. And for a closed system, so a pressurized system, we would say about 103 to 105 degrees. Again, this is all by returning the condensate. Hopefully that answers that question.
Thank you.
So, yeah.
If there's no more questions, you can proceed. Yeah.
Okay. So water hammer. So the problems, how do we recognize water hammer in our systems? So you have noise, you have vibrations, you have damage to bracketry, so maybe brackets breaking that are supporting pipes, and damage to capital equipment, so effectively damage to control valves, damage to traps. Many of you may have heard the banging you hear on a water pipe. That's water hammer. So the cause here, so failure to remove condensate from your steam pipes, insufficient fall in pipes. So we try to maintain over steam lines a 1 in 100 fall. So that means for every 100 meters, it will drop by 1 meter. Waterlogging due to poor trap selection, so effectively your condensate is building up. Waterlogging due to poor trap sizing, so the trap is too small to clear the load that you have. Use of concentric reducers, so effectively these ones where you create a step. Incorrect strainer orientation. So I'll start from the top. So when we have water hammer, effectively we have water in the line. As the steam moves over the surface of that water, it picks up speed. So there's a friction that goes on there picking up the water. That then over time will produce a slug. You have steam that builds up behind it, which then pushes this slug down the pipe, and then you'll hear the bang where it hits a bend or a closed isolation valve or a piece of equipment. So that's how water hammer is forming and where the sound is coming from. That can be quite dangerous as well. So if you think of Tom Cruise, I refer to him quite often in Top Gun, driving his fighter plane or flying his fighter plane. At times with the older ones, he could be doing Mach 1, a speed of Mach 1. So that slug in that pipe can be doing that same speed as that fighter plane. So 1,000 miles per hour, I think that is, isn't it, Mach 1? So concentric and ecocentric reducers. So ecocentric here means that you effectively got the reduction on one side, so you maintain a straight fall in the pipe. If you have a concentric and steam is coming this way, you create the step, which effectively allows a build up of condensate. If it was coming, steam was coming the other way, you wouldn't have the issue because you've got the drop. Incorrect installation of strainers. So as we were saying earlier, a condensate trap should be vertical. So this should be facing downwards as it shows in the picture. This allows the particles to come along, catch in the strainer, and then the condensate pass along without actually taking them with them. With a steam trap, we don't want the buildup of condensate in here because that could then produce the slug. So we would have this strainer facing towards us, so there can't be a collection of water. So again, here solution, audit, monitor steam traps. So checking your steam traps, making sure they're working correctly. Correct fall in the steam pipes, as we said, that 1 in 100. Check strainer orientation, referring to here. So you've got one for steam or gas applications and then liquid here. Check correct reducers. So let's talk about the ecocentric and the concentric. Consider auto condensate draining for startup. So that would be this trap here, which I will touch upon after the last point. And check steam system startup time is long enough. So are you giving your system long enough to warm up before you start opening those isolation valves? So this is what we call our number 8 trap. So we would suggest this for mainline drainage. At some point when you're warming up your system, there is somebody whose job it is to open all the isolation valves on your pockets to allow the condensate to flow out as the steam system warms up. They then have to go around that system again and slowly close those off. By putting this device here, because this closes at 100 degrees, it uses a liquid filled capsule in here which expands and contracts. So you've got your condensate that flows in. As it starts getting to 100 degrees, to the point where it's reaching steam, this will expand and close off the drain. This is perfect for you in conjunction with those isolation valves. So you'd have the isolation valve, but it will remain open. You would put this in this orientation as well, so horizontal orientation. And you would then use this to drain the condensate from your system on startup. So does anybody have any questions before I get to the next slide?
Yes, we have 2 more questions, and I believe maybe you may have answered this one, but are there specific scenarios or conditions that increase the likelihood of water hammer occurring?
Yeah, so effectively any system or any allowance of wet steam in your system will produce condensate in your pipe, in your steam pipe, and that will then carry over into a water hammer or can cause water hammer. So if you have insulation that's broken down, so it's cooling your steam system, it's creating condensate on the inside of the pipe, that eventually, if it's not drained properly, will cause water hammer. Trap failures where they're closed, where they failed closed, will introduce condensate into your steam system. by effectively build up. Again, lack of separators. So if you have wet steam from, say, carryover from your boiler, and incorrect drainage or not enough drainage, we recommend as a point on main lines drainage, you should have a trap set every 30 to 50 meters to maintain dry steam. So if you don't have enough traps, you'll end up with wet steam and therefore the potential for water hammer. Did that answer that question? I think there was 2 parts to that, was there? Or was that?
That was basically it was if there are specific scenarios or conditions that increase the likelihood of water hammer occurring.
Yeah, so again, like we were saying, so bad insulation, trap failures, equipment, lack of separators, those kind of things.
Yeah. So the second question is what role? Yeah. So the second question is what role does Mach number play in the behavior and performance of steam systems?
Sorry, can you repeat that?
What role does Mach number play in the behavior and performance of steam systems? Mach number, I would believe this is the ratio speed of an object to the sound, MACH.
Yeah, so the Mach speed. Yeah, so it's damaging. So say you have a float trap and you introduce water hammer there. So the float trap works by a ball that floats on top of the condensate. As the condensate rises, so does the ball. That opens the trap and allows for the clearance of that condensate. If you have water hammer, so the Mach speed that's in there, you effectively hit that ball with energy, which is the water in this case, which is non-compressible. So it's like taking a hammer to that ball. Over time and enough speed, enough energy, you'll collapse the ball. So it will sink in that trap and it will fail closed. You then could see the same kind of damage on control valves. So if you have water hammer on a control valve, you can damage the stem seals. So you'll see leaking from the stem coming from the bonnet. You can damage the seat itself. By having a control valve, you can also introduce water hammer if you have condensate in your system. So when it opens, there's suddenly a slug of water that passes down through it, just like opening an isolation valve. That can hit sensitive equipment, say like a filter. So it will rip through a filter, it will damage baskets and strainers. The faster it goes, the more energy it releases when it hits a surface. So the in relation to the speed is energy, effectively. You're giving more energy, more force that it's going to hit something. We, as a global company, would recommend SG iron used as a minimum grade instead of cast iron. The reason being is, as we touched upon before, with microfractures, if you have a steam trap which is seeing water hammer, it's being hammered effectively, hence the name. The material is being hit hard. It can introduce microfractures, so fractures you cannot see. And then at one point it will give way, it will split. If that's in a confined environment, say you have 7-bar condensate, now all that condensate suddenly turns to flash steam. It fills the area because of the volume. It could be potentially dangerous, life-threatening. I remember hearing a story of a gentleman who was working, I won't say in what area, but it was there was an isolation valve for the main steam in a roof void. So he had recommissioned the system and it was meant to slowly open this isolation valve. It's cast iron isolation valve. It had been there for a while and hadn't been inspected. So he opened this a little too fast. It cracked. It fell apart. It filled the void with steam. And I don't know if you guys have ever boiled a chicken. That's effectively how he was after 4 minutes. So they had to scrape him off of the roof. That's the dangers of water hammer and incorrect material use. Sorry, that was probably a little bit graphic for the warning. Sorry. Hopefully that answers that question.
I do believe it has answered. Also, I do believe there's no other question, but also we're looking at time, so we may need to.
Yeah, no problem. So we do listen to your feedback. Many of you have said that the course is maybe a little too short. We do have restraints on our business, so we try to make these as long as possible. But equally, we do appreciate it's very difficult for some of the managers in your areas to release you for a longer period of time. So in-depth training on any of these subjects or other subjects is available from request through our office. So you can contact me, Anthony, Cornelius, the business itself, and we can arrange for training to be done on the subjects we spoke about or other subjects more in depth at your premises. We also offer free online correspondence courses. So these are courses you can take an exam for, you can get the certification for via written correspondence. And we can supply a wide range of engineering books. So as you can see there, what we call the Bible is the steam and condensate loop book, and we have our metric steam tables. So I would just like to take the time and thank you all for joining us again on this third installment, and please feel free to contact us with any questions or any information you require. I will then move to the next slide. You can reach us on any of these contact details. So as you can see, myself and Auntie are there. Cornelius helps with South Africa and the wider audience too. So please take note of those numbers and those email addresses and send through your questions if we haven't managed to cover them. So over to you, Anthony, for close down.
Yeah, thank you, everyone, and we really appreciate your attendance to these sessions. And I would really advise, please fill up the form at the end of the session. As Nick has mentioned, it is our way of getting feedback to you and knowing how we can improve on these sessions. So I do once again thank you very, very much for attending this session. And if you have any other questions, please feel free to ask or email us, and we will be able to get back to you. Yeah. So if there's no other question, then I think we will close this live event. Thank you very much.